Hello, everybody. My name is Jean-Marc Jezekel. I'm a professor at the University of Rennes. I'm a vice president of Informatics Europe. So it will be my pleasure to introduce Professor Marlon Dumas here. But just before his talk, just a quick presentation of Informatics Europe. So Informatics Europe represents the public and private research community of informatics in Europe as a continent, not as a political thing. And we want to create a strong common voice to safeguard and shape quality research and education in informatics across Europe, and to promote concerted position and acts on shared priorities in the areas specifically of education, research, knowledge transfer, and social impacts of informatics. So we have members, more than 160 institutions from the best institutions across Europe, from 34 countries right now, and we are expanding fast. Our goal is to foster quality of research in education and informatics and to promote pan-European knowledge transfer and collaboration between academia and industry and society, including government and public institutions. We want to engage with society on the nature and impact of informatics, and now that there are many issues with the use of privacy, cybersecurity, and the like with informatics. And we want to promote quality standards and best practices in research, education, and knowledge transfer. Our activities are mainly performed by scientist volunteers through permanent working group in areas. This is evolving, but the current areas are, the most active areas are education, diversity, social impact, policy recommendation, data analysis and reporting, and member empowerment through academic leadership, knowledge sharing, and networking. And we have, when it is needed, complement specific ad hoc task forces for that. We have several events across the year. The most well-known event is probably the European Computer Science Summit, which is typically in October. So the previous one was in Madrid, but the next one will be in Hamburg. So you're welcome to attend. And we have this webinar series, which this one is in one instance, with distinguished keynote speakers. And we have various areas of informatics. And we also have academic leadership development courses with the spring, this spring cohort that is now open for registration. So everything is on the website, and we won't take more time on that. To switch to the introduction of Professor Marlon Dumas, who makes us the pleasure of giving this seminar. So Marlon is a professor of information system at the University of Tartu in Estonia, and is also a co-founder of Promore, a spin-off company that develops open source solutions for process mining and optimization. So Marlon Dumas was born in Honduras, the place of the Maya, if you don't know. He got his PhD from Grenoble University in France, and after graduating, spent a few years in Brisbane, Australia. And for reasons yet to determine, he decided to trade the sun for the gloom of moving to Tartu in Estonia. He's a world-renowned expert on information system engineering and business processes management. And there is, in particular, his well-known book on fundamentals of business process management. So his research focuses on data-driven method for business process management, including process mining, of course, predictive process monitoring, and data-driven process simulation. He is recipient of an advanced grant from the European Research Council with the mission of developing algorithms for automatic discovery and assessment of business process improvement opportunities from execution data. So Marlon, thank you very much again. The floor is yours. And if you have questions, there will be a Q&A session at the end. So prepare your question, and if you wish, you can put them in the chat. So Marlon, the floor is yours.
Thank you very much for the introduction, Jean-Marc. As was announced in the introduction, I am Professor of Information Systems at the University of Tartu, and I have been very active in the past 20 years in the field of business process management. Out of those 20 years, in the past 10 plus years, I have been active in a subfield of process management called process mining, which is about using data to improve business processes. Along the way, I spinned off my research into a company called Promore that effectively is taking outputs from our research on process mining into a commercial practice. Today, I am going to talk about one very long-standing problem in the field of business process management in general, operations management more generally, and particularly in the field of process mining, and is about constructing accurate and reliable machines that are able to help you to do what-if analysis on your business process. And it's a very open question that existed when I started my career back in the late 90s, and it still exists, and it does not have a solution. It's a very applied problem. It answers questions that managers have everywhere in large or medium-sized organizations, and for which several approaches have been tried, and so far nothing is satisfactory. And that justifies that, is it achievable at all? So the problem is the following. Organizations, perform a number of so-called processes in order to fulfill their functions, particularly to serve customers or to generate reports for the tax office in order to pay their taxes, or reports for the National Statistics Office, in order to fulfill certain obligations. Banks, for example, are obliged to check that the transactions that are being made through the bank are compliant with anti-money laundering regulations. And they are running lots of processes to do that. A bank will run processes for handling loan applications whenever you make a loan application, and it has to go through a certain number of steps. So as soon as you have a medium-sized company of a certain level of complexity, there will be non-trivial processes out there. And over time, in order to deliver best possible service to the customers in an efficient and effective manner, and to comply with regulations, organizations assign dedicated managers or teams of managers to each of their processes. So for example, I have here a very simplified process for issuing credit to a customer in a bank. That process will have a process owner, which is a manager or a team of a manager and several analysts, whose responsibility is to make sure that this process, which is executed perhaps hundreds of times per day, is delivering the best possible value for the customers in the most efficient and in the most effective way. And things are not stable in an organization. The company is not stable. The organizations are not stable. By the way, I hope I am sharing my slides. If not, please ping me, but I hope it's all fine. So it is all fine. So organizations are not stable. COVID comes, you have higher demand for some products, lower demand for other products, and you have to adjust your process to remain efficient, or you have workers who are absent, let's say for 1 week due to COVID, and 10% of your workforce might be off because of Omicron, and you have to adapt your processes to those circumstances. So there is continuous change in a business process. So it's not a stable animal. It's a changing, always evolving object, a business process. And in this context, companies have very often, or process owners have very often the question of like, well, what can I do because of some issue that has come up in my process? Should I reallocate people or resources from one task to another? Should I hire additional people? Should I try rather to automate certain tasks in the process? automation technology has taken big strides in the last couple of decades. So it's possible sometimes to achieve more efficiency, better data quality by automating certain activities. Should I rearrange the way certain activities are performed or the relative priorities, etc.? What can I do? So they are not short of ideas. I mean, they are always thinking about, I could do this, I could do that, I could do that. And their most recurrent question by far is, if I do this change in the process, if we start doing things in this way, by how much will the business process improve? Will it improve? By how much will it improve? So that's roughly very simple. Now, for a simple business process like this one, there is no need for any computer assistance, but in reality, processes are more complex. They can look like this if I want to capture as a process model, or rather a business process in its full complexity looks like what I'm showing the screen now. And if you really want to take into account all the corner cases, all the exceptional paths, all the different types of loans or customers you have to deal with, and the different types of exceptions that can handle, that is what you get. So we need to be able to answer this question in a rather automated way, possibly in a data-driven way. The traditional approach to this question, dating back from having roots in the 80s and 90s, is business process simulation. So what is business process simulation? In essence, it's about building somehow, one way or another, building a business, a model of the process, like the process behaves this way usually, the process is performed by these people, and then conceptually running it stochastically, a large number of times, like drawing random numbers and simulating the fact that the process is running according to the business logic that is encoded in a simulation model. So in the 90s, when I started working in this field, late 90s, early 2000s, there were analysts, coming out from schools of business and economics or finance, etc., who will be capturing these processes and just spending a month, 2 months, 3 months building up these simulation models. Well, it turns out that that was later not successful, as I will tell you. So the starting point, the first thing to understand is that a simulation model of a business process includes quite a lot of things. First, you need to have a very accurate model of your process in terms of which activities are performed and how are these activities related to each other. What are the temporal constraints between these activities? In which conditions should activity be performed or not? That is called a business process model. So business process modeling per se is a very time-consuming task, very error-prone task, and you never get a perfect model of your process. You will always leave some exceptions aside. But in addition to that, to be able to simulate it, you have to accurately capture the temporal dynamics of every task in the process. How much time this activity takes to occur, how much time this other activity takes, how much time this activity takes. So you can use sampling, observations, and statistical feeding to try to model these different execution times in this process. For very mechanistic processes performed, for example, in a manufacturing line, this is feasible. For processes that involve human beings, it's trickier. In addition, you need to specify, for example, how often do I get a new loan application into one process? How often do they arrive? With which distribution do they arrive? When do they arrive? Do these loan applications arrive anytime or only during business hours, etc.? We also have to capture branching probabilities. In what percentage of cases, when you reach a certain point, the process, do you go left? In what percentage of cases do you go right? You have to then capture the resources, people in your process. Which teams or individual people work in your process, who is responsible for which task, when do these people work? Usually they don't work 24 hours 7, they work under certain timetables. With COVID, it's more complicated because people don't really work under fixed timetables. And if you want to capture the temporal dynamic of the process, you have to get all of the previous pieces right. And that is not realistic. The process models, the business process simulation, for it to work, it assumes that the process models that you will draw are perfect and authoritative, always followed by the letter. There are no deviations in real time, in real life, no workarounds, or that those workarounds can be ignored because they are not too frequent. It requires that the simulation parameters, all these waiting time, distributions of processing times I showed you, arrival times of new cases in the process, they need to be modeled very accurately. More often than not, in practice, people are doing guesstimates to figure out what these distributions look like. We require for simulation a number of other assumptions, that a resource is only working on one task at a time, like no multitasking. Very often we require that resources do not suffer from fatigue effects, from external interruptions, distractions, etc., or that these distractions are sufficiently infrequent or sufficiently stochastic that they make the process goes in both directions, such that ultimately they cancel. That is a very strong assumption. You assume that every person is the same. No two people are the same. Two robots can behave more or less the same in a factory line, but two people don't behave the same. Every person is an individual different from the others. And also it works very well when people are dedicated to doing the work in one process, but people don't do that. People are alternating between doing something for one process, something for another process, something that has not anything to do with any documented process, etc. Ad hoc things are happening all the time. So the idea that there is going to be an analyst, like a quant, who is going to come into the company, capture a business process as a diagrammatic model, and add all these simulation parameters by collecting data manually left and right, just does not work. So when I was early in my career, I saw companies dropping the idea of I do simulation, and then I saw case studies, research papers where people were saying, well, simulation of business processes as we know them, that involve people and so on, is hopeless as a discipline. There are so many pitfalls out there in simulation that it's impossible to deal with them. So end result is business process simulations that are based on incomplete models, guesstimates, simplifying assumptions are not faithful enough to be adopted in practice. The adoption of business process simulation, as of now even, is rather disappointing. So back in 2008-9, together with some colleagues that were working in the field of process mining, we had the idea that maybe we could use data to semi-automatically, perhaps automatically, come up with better simulation models. The idea is that the work that these people are performing in a business process is being recorded in different systems. If you put an insurance claim to your insurance company, all the work that is being done in the back end is recorded in an insurance claims management system. The same thing for a loan application. Or if a company receives an order, for example, via its e-commerce front end, all the work that is happening done by the clerks or in the warehouse, etc., is being recorded in different types of enterprise systems, such as customer relationship management systems or CRM systems, or other types of systems called ERP systems. These systems are designed, fortunately, in a way that they remember everything that has been done in there, every invoice that has gone in, every approval of an invoice is recorded somewhere there. Maybe not always, but say most of the time. So if we extract tables from this log that tells me which activities are performed by whom and when and to which business process execution they relate, that's called an event log, then I can do a lot of very interesting things. Those very interesting things is what we call process mining, which is like data mining techniques specifically to analyze data about the execution of business processes. So let's say I have this data. What do I want? I want that if I name you one or two business processes in the organization for which I have some form of maybe partial specifications, like partial process models, not perfect ones, but something. And if I give you some data about this business process from an enterprise system, and I tell you that I want to analyze the execution times of my process, or the resource workload, or the labor cost in my process, and then I tell you, what if I do a change? What if I add 3 more people in a certain resource pool of my process? What if 10% of my workforce reports sick because of Omicron next week? I would like you to predict what will be the values of these performance measures like time or cost on my process after this change occurs. So after this change happens, what will be the impact on those performance measures? I don't necessarily need to know everything that will happen, but I want to know what is the impact on those performance measures. And naturally, I want that, because this is a prediction problem, I want that these predictions that this machine will do for me about what will happen if I change something, I want those predictions to be accurate. So, if I define some error message between error function between predicted and actual values, I want it to be as small as possible. And second, I want ideally these probabilities to be reliable, or at least to have some reliability estimates that tells me some confidence intervals, for example, that tells me how much I can trust a given prediction. So that is the problem I am posing today, and for which I'm going to sketch some research directions leading to the open question, can this be done in such a way that it just achieves these high-level requirements in practice? So the approach that we started exploring with several of our colleagues in the field of process mining, and I guess this has been going on for 12 years, is called data-driven business process simulation. So we are going to build a simulation model, but we are not going to require someone to manually design it. We are going to automatically derive it from the data. So these tables I showed you before that I extract from a system, I'm going to take them as input to a learner who is going to produce a simulation model. Possibly along the way, it's going to use some knowledge, like constraints on the process, things that cannot happen, or maybe a process model that partially captures the main pathways in the process. So I'm going to take that knowledge, if I can represent it in some way as input, and I'm going to produce a simulation model. Then I'm going to specify a change. So I need to have a language for specifying changes in the process. What if I add a resource? What if I add a new activity? What if I change a certain order between two activities? I'm going to specify that change in some domain-specific language, and I'm going to feed the simulation model and the change specification into a simulation engine, which is going to make a prediction. And I want that prediction to be accompanied by a reliability estimate. So the main machines here are the simulation engine, but simulation engines is a very well understood topic. We know how to build such discrete event simulators. the topic that is of interest is how do we learn this model and how do we ensure that it's accurate and reliable. So there has been a lot of work about it, and I'm going to be a little bit egoistic now. I'm going to present only the approach that was developed in my research group, but bear in mind there are other approaches in this area that have are equal set of merits, or different sets of merit, different trade-off, but it's about the same. So we're going to present you one example of that machine. It's called CMOD, that takes an event log and then discovers a process model out of it using a set of techniques called automated process discovery. Automated process discovery is a set of techniques that have been developed in the field of process mining that take data from enterprise systems and produce you graphical process models out of it. And they ensure that this graphical model is relatively accurate relative to what I observe in reality. And then we apply a set of techniques, usually known as model enhancement techniques, to fit curves on the execution times of activities. So we do a lot of curve fitting on the arrival times, and we use techniques for discovering calendars. So you give me data and I tell you of somebody doing work, and I tell you what is the calendar under which this person works, etc., etc. And I assemble these things. That's what CMOD does. And it produces a simulation model that it fits into a simulator. Along the way, CMOD uses different techniques that have a number of parameters. Every automated process discovery technique has parameters like, for example, the level of filtering, the degree of sensitivity to concurrency, etc. Every curve fitting technique has certain parameters like, your tolerance during curve fitting, etc. Every one of the about 12 techniques that CMOD uses to discover a simulation model has certain parameters. So we do something similar as what is done in the field of machine learning. We take an initial simulation model as if it was a decision tree, for example. We assess its accuracy on a validation fold. So we separate the data into training validation. We assess the accuracy on the validation fold, and we plug in a hyperparameter optimizer, for example, a Bayesian optimization technique, to try to come up with new configurations of the parameters that hopefully will give me better accuracy. And for that, of course, I need to have a way of measuring the accuracy of a simulation model. I'm going to skip technical details and just say that, to summarize, we take an event log, a data set of the business process running for a period of, let's say, 2 years. We partition it into training set, validation set, and testing set. We then discover a model. Lots of technical details about how you discover a simulation model using process mining techniques and statistical curve fitting techniques, but that's just technical. We generate, and then we use the simulation model to generate an event log, meaning we simulate, say, 10,000 times, and we get a data set out of the simulation. This is how the process was executed during the simulation. And then to measure how accurate the simulation is, we compare the log that was the data that was generated by the simulation with that validation fold that I took away when I partitioned my initial log into pieces, so into folds. And now I need to compare an event log that is simulated with a fragment of a real life log, and I need to know how accurate the simulation is. Well, you can do that by defining some measure that takes into account the string eddy distance between the words that the simulator generates, because you can see the executions of a process as a set of timed words. So you measure the distance between the words that the simulator generates and the words that you observe in reality using a Damerau-Liebenstein distance. And you can refine it in different ways to take into account the execution times, who is allocated to which resource, etc. Because the DL distance is a parameterized distance at the end of the day. You can put in whatever cost function you have. So we defined some concepts of similarity between the log generated by a simulator and a portion of a real-life log, which we call control flow similarity measures or temporal similarity measures, so that we can measure how accurate the logs generated by the simulator are with respect to reality. This is a crucial piece. Once you have this, you can then not only assess the accuracy of a simulation model, but you can also optimize it using a hyperparameter optimizer, because what you have defined is effectively a loss function. So using string edit distance as a basis. So we have all sorts of measures. We call them, for example, business process, event log similarity measures that we have defined on top of this. We did an empirical evaluation where we take CMOD, we take a data sets, we take CMOD, we generate a simulation model, and then we test it against a testing fold to check how good it is after all the hyperparameter optimization. And we throw in a fair amount of hyperparameter optimization to it. And these are string edit distances, think about it, between the simulated log and the real log. More sophisticated than that is timed string edit distance. So I'm taking into account the timestamps in the distance. So this column here is a pure string edit distance, and this is a timed string edit distance, so 2 columns. And we did this actually on about a dozen logs. I'm only showing about 7 of them here, of different levels of complexity. And we found that the simulation models we discover using CMOD resemble the real life by something ranging from 29% to about 57 or 69%, depending on the event log. And sorry, these are distance measures, so lower is better. So 0.29 is pretty low, which is good. Well, not maybe good, but okay. So the distance between the log is 0.29 out of 1, and 0.69 is pretty bad. That was because it's a process that has a high level of variability, very complex process. And then we found that it's not good at all. Even if we take into account lots of different factors, make the technique very sophisticated, it's really not very good. So, then we thought that maybe it should be possible to do better by combining perhaps process mining with deep learning techniques, because deep learning techniques don't really care about what is causing the waiting times. So I don't have to capture all the mechanisms that cause waiting times in a process. Instead, I can let a deep learner learn the waiting times without having to inject or codify the mechanisms that cause waiting times into that deep learner. And there are some work that has been done on learning deep learning models from event logs of business processes. So to tell a summary of the story, what we did is that we took those deep learning techniques and we basically combined them with CMOD. So in order to generate mixed models that use simulation on the one hand and deep learning on the other. And there are some things we have learned along the way, and I'll try to summarize those things. I cannot present all the technical details. We will share the slides and you have some pointers and you have some further technical details, but there are 2 things that we have learned a lot along the way. The first thing is deep learning models are pretty good at capturing the temporal dynamics of the process in its as-is state, so the current process, much more than simulation models can do. Because they just learn to fit what is in there without caring about what causes those times that we are observing in a business process. So we have also learned that simulation models are fairly good. So data-driven simulation models using process mining techniques are fairly good at capturing the order in which activities occurs, the possible sequences of activities, and also who performs which activity. But they are not less good in terms of predicting times. So our idea, which is what is ongoing work, is how can we effectively combine simulation models, discrete event simulation models discovered from data using data mining or process mining techniques with deep learning models discovered from the same data, with the caveat that simulation models are designed from the ground up to make what-if predictions. What happens if I do this change? What happens if I do that change? Deep learning models are built to capture the as-is, but they are not very good at telling you what will happen if I do something I have not seen before. So we did that initial exercise and we proposed something called Deep Simulator, which is the same thing I showed before CMOD, but we inject a deep learning technique to learn the timestamps at which different activities during the simulation occur. There's a fairly sophisticated exercise there to assemble these two things. Again, I skip the technical details. They are mainly at a technical level. And then we found that in an as-is scenario, deep learning, the deep simulator outperforms the CMOD technique. So combining data-driven simulation with deep learning is better than only data-driven simulation alone to predict the current state of the process, how the process currently behaves. That is fairly encouraging. But then once again, I skip the technical details and leave it in the slides, but once we experimented about what if I do a certain change in the process, can the deep learner understand what will happen in that case to the execution times in the process? And we found that in two cases, if the number of case instances increases, meaning what happens if the number of loan applications increases or decreases, it turns out that the deep learning technique is fairly good at making predictions out of it because it learns from the variations in demand in the process that have been observed historically, and it can project them into the future. But then we did an experiment where we tried to introduce an activity into the process that we had never before seen. And we tried with different ways of capturing the deep learning technique, like embedding techniques, different types of embeddings, etc. And essentially, the results are that capturing variations in the demand of the process, in the workload of the process, using deep learning techniques works fairly well, but capturing changes, like introducing activities that have never before seen before, seems to be very problematic for deep learning techniques. They just cannot figure out what is the impact of inserting an activity that has not been seen before in the middle of the process, no matter what we have tried, but maybe we have not tried the right techniques. Very difficult practical problem posed at a relatively high level, of course, can be refined in different ways, but it's a very exciting, difficult problem, how to construct accurate state of thinking in the field is combining, automated process discovery techniques with deep learning techniques. But there is a very difficult exercise to be done at the intersections of the two, particularly to make the deep learning technique extrapolate on things it has not seen in that particular form before in the data. So the generalizability problem is hitting hard here, is making us hit some hard boundaries. And of course, all this needs to be validated more extensively in real case studies, and that's basically what we are working on. And that's basically my presentation for today, and I will be very, very glad to take in some questions from the audience in case you want me to zoom in into one of the points I made.
Well, thank you very much, Marlon. It was really interesting. So I don't know whether people have questions. Yes, I see some hand raised. So did you raise your hand, Pekka?
No, I was just clapping for the.
It was clapping.
Appreciate.
Sorry, my mistake. So any question, you can either ask in the chat or raise your hand. If not,
I see
yes.
Anastasios, yeah. Please.
Thank you very much for your interesting talk. It was very insightful. And I'm from Aristotle University Thessaloniki, working on these topics. And I noticed, I enjoyed your talk very much, but I noticed that you tried to avoid the term digital twin. Do you think that digital twins for business process are going to be something different, a step further, or exactly what you described, but you just didn't say the word?
Yes, thank you for the question. So the same presentation, I sometimes give it to an industry audience and sometimes to an academic audience. And the main change I make is digital twin versus data-driven simulation. Yeah. So there's a big intersection between the two concepts. In the academic community, we are used to discrete event simulation, and if you discover those, or if you drive the simulation with data, you would call it data-driven simulation. And in the industry world, particularly because of Industry 4.0 type of trends, this is called a digital twin. And if it's a digital twin of a process, I tend to call it a digital process twin. Yeah. And the concepts overlap, except that, well, data-driven simulation corresponds to a particular type of digital process twin, one that is capable of what-if analysis. Because there are also some digital twins that are purely there for monitoring and for, so just replicating what is in the real world in order to just find problems during the execution prior to actually running the thing. Yeah.
Thank you very much.
Maybe I have one question on the way you're using deep learning for doing that. The thing is that, I mean, maybe it's a naive question, but did you try to compare with, let's say, a pure deep learning approach where you do not try to learn the structure of the process, but just the outcome in terms of, the time it takes, the total time it takes, or the cost, or the resources, or something like that, and putting all the parameters as features for your learn model, and then just be interested in the net result. So I'm wondering whether that kind of naive or straightforward approach of using machine learning without entering into the details of the structure of the process, but just the overall result, whether you would have tried that, or whether there is a good reason for that not to work at all, or what do you think?
Yeah, I guess that there are different variants of this problem. There is one where, let's say, I am only interested in the end-to-end execution time. That's the only performance measure. I don't care what is the waiting time of every activity. I don't care in which activity, in which order the activities are performed. I only care about end-to-end execution times.
Yes.
So in that case, you will have a particular metric, and you could confine yourself to that, let's say, restriction of the problem, and then develop techniques specifically for that. So, and there, I'm assuming that in the assist case, so to predict the execution times in the assist case, to replicate the assist, it's gonna be very good approach. But I'm still having troubles to understand how you will make the deep learner generalize. What if I add 2 activities in the process? What's going to be the impact on the execution time of the whole process? I see that variant of the problem. It's a restricted variant of the problem. So I don't try to predict everything, but just like some top-level performance measures. I think I have not explored that variant of the problem. I think you will stumble upon similar issues as the variant we're currently tackling, which is I really want to replicate the process. I want to have a machine that can replicate the process in its entire, more or less in its entirety.
Okay, thank you very much. Maybe Professor Koschmider.
Hi, Marlon. So 2 questions. So one question what I was asking myself is, so your research question is to provide a solution that is accurate and reliable. And one slide you showed that you have your, let's say, real log or real simulation model, and then a process model that you compare. And then I was asking myself, would it make sense not to compare the similarity, but rather the dissimilarity between them? Because what you're doing is then, for instance, you have a historical data that doesn't correspond with maybe, let's say, the process model that was the right one for the time frame. Do you know what I mean? Yeah. Like, for instance, some conditions, some context changed. Yeah, and then you compare different maybe time period and different context factors, the influences, both the event log and the process model.
Yeah, I gather. I'm not quite sure if, I mean, whether you use a similarity measure or distance measure.
Not dissimilarity.
What?
No,
Yeah,
dissimilarity.
Dissimilarity.
So what's not similar, but what is dissimilar between them?
Yeah, I guess what you can, the idea you are putting in the table, which is very interesting, is that, let's say I tell you what will happen if I do a change. And what would you do? You will try to find that change in some similar change happening in the past. So in your historical data, you will find like the most similar change or some components of that change in the past. You will then learn from what has happened in the past when such a change occurred, and then you will extrapolate to that change. And that could be an interesting twist on that problem. I believe that is why this deep simulator works well when you change the number of cases, the intensity of arrival of cases. Why? Because in the historical data, you probably have observed high periods, peak periods, and low peak, like high intensity and low intensity periods. Then when you tell to the model what happens if I create more instances, somehow the deep learner manages to make a good prediction because it can learn from what it has observed in the past. And I think your hint here, and that's a very interesting twist on this problem, is try to look, whenever I give you a change, try to see similar changes in the past, and look at the period before and after the change and learn from it. Yeah.
That's one issue. And the second issue, so one of my colleagues, he is an expert in deep learning, and how he enhances his technique is always with human in the loop. So as far as I understood, you only use deep learning here in your approach. So what you might consider is to use, let's say, a human in the loop approach that says, okay, you have this result, and somebody say yes and no, and just to see if your accuracy improves. Because since you assume, or since you claim to be that your approach is reliable and accurate, so that might be some, let's say, some points how to approach towards your aim. Just only one idea.
Absolutely, absolutely, and yeah, I can only agree with that statement. I guess that we have been trying to stay in our corner so far and try to do as much as we can automated, but maybe it's time to move on and to bring the human in the loop, as you say.
So if you're looking for co-authors, just contact me.
I think you just mentioned 2 papers that we need to collaborate on.
Okay.
Thank you very much. So maybe we have time for one last question. Elisabetta?
Yes. First of all, thank you for the nice talk. It has been very interesting. My question is related to the way you collect your log, because essentially I was thinking, what happens when you try to apply a similar machinery into a different context? For instance, in the software development process in which people is using multiple different tools, so for instance, continuous integration tools and others, and you might be able to collect some kind of event logs, and you may able to use the same kind of approach, at least from the high level of abstraction, to that specific type of process, which is not necessarily business process. So I was wondering whether whether you are making specific assumptions on how your logs are collected, and whether you're assuming that there exists a specific business process management system, or whether we could imagine a more, let's say, a less, let's say, an unconstrained or limit or not too much constrained context in which you can capture events and data from multiple sources. And in this case, what kind of data you would need to address this point?
Yes, so the answer is somewhere in between those extremes. So we do not require that the data comes from a specific type of system like a BPMS, and the logs we use in the experiments come from a diverse set of systems, ranging from hospital information systems to CRM systems, ERP systems, and so on. That's one part of the answer. There are some constraints on the data. So I need to have execution traces of a process, completed ones. So I need to see how different instances of a process behave start to end. So I need to have a concept of, like, there is a process, it has a start, it has an end, it's executed many, many times. And I can extract trails from the moment the process starts to the moment it ends, with a lot of activities in the middle. The more you put in, the better it is. And for every activity execution in one of those trays, I need to know when it starts, when the work starts, when it ends, and who does it, which resource does it. Those are the requirements. And there are probably lots of other systems than what we have considered where you can get such data. So there is potentially more applications of what I have mentioned here than business processes. Perhaps equally well, this is applicable in some software processes, software development processes, for example, definitely in industrial processes. We have not explored the full range of possible data sources, definitely. And that is something, I guess, that will come with time as we get some results and we manage to attract neighboring disciplines to work on this topic.
Great, thank you. This might be in the future another topic for another paper, maybe.
Yes, definitely.
Okay, so I think time is up. So I would like once again to thank you very much for this great talk and great presentation. I mean, it was very, very, very good and very interesting. So thank you very much.
My pleasure. My pleasure
for attending this Informatics Europe webinar.